Hi guys, Buildzoid here, and today we're going to be talking about the power delivery on the RTX 3090 Vision more, because yeah, I got the card fixed, and now that I have a card in hand, I've had the opportunity to poke and prod around the power delivery circuitry to see how it's set up. Um, well, I'm not very impressed by how it's set up, so we'll get into that. But before we do that, well, for illustrative purposes, we're going to be using the Gigabyte RTX 3090 Eagle OC PCB here. Mostly because for some reason, I've not, remembered to take a picture of the PCB of the Vision at any point that I had it disassembled. And I don't really want to, take it apart again. Um, yeah. So we're just going to use the PCB pictures of the Eagle OC here because this is actually the same PCB. There's just a difference in the capacitor configuration behind the core. Um, yeah, so the first thing we need to address is that the very first video that I did about the RTX 3090 Vision, I made two mistakes in that video. Mistake number one is that I said the UP9511 controller is controlling the memory rail. It's not, it's controlling vCore. Why the cheapest controller on the card is controlling the most important power rail, I have no idea, but it's an NVIDIA GPU, so I can't be too surprised, I guess. And the other mistake that I made is I said that this PCB configuration is, relatively custom by Gigabyte, but that's not true because if we look at a real reference 3090 here from Palette, you can very clearly see there's an option for a 10th power stage in the vCore VRM right there, and I just completely forgot that is a thing. For some reason, I was like reference 3090s are 8-phase with the option for a 9th power stage. No, they're this is still 8 phases, and this is also 8 phases, but this is 8 phases with 9 power stages, and Gigabyte has gone ahead and populated that optional 10th power stage. So, this VRM configuration here from Gigabyte is not some crazy Gigabyte creation. This is just sort of Gigabyte fully populating the reference design. As as provided by NVIDIA, basically. They have obviously not used the same PCB though. Like if you look at this palette card, you can see that this thing is designed to take through-hole inductors, SMT inductors, through-hole capacitors, SMT capacitors. Like this PCB here is basically designed so that if there's any component that you can't get your hands on, you can just use a different component instead. Whereas Gigabyte has really sort of, set up the PCB specifically for the components that they actually intend to use, which the reference design just kind of is set up so that you can use whatever happens to be available at the time. Not that that's necessarily a bad thing, right? Like, as long as the components meet spec, it's just like, yeah, use whatever. Anyway, yeah, so that was the two mistakes I made in my first video. Is like, one, this is actually more reference than I said it is. And two, the 9511 handles vCore. It doesn't handle the memory rail. Anyway, let's talk about how that 9511 is configured, or more important, more specifically, how the power current limiting is configured, because yeah, it's not great. So, let's talk about first the total output current protection, and we're just going to read this. So, the UP9511R provides total current over current protection as shown in figure 11. So basically we have this lovely circuit here, which handles the total output current protection. So basically, limits how much how much current can be flowing through all of the phases. Actually, it doesn't limit how much current can be flowing through all of the phases. It basically, what this does is, if you pull too much current through all of the phases, the VRM shuts down. But anyway, and that's explained here. So the sensed current ISUM is mirrored internally and fed to the IMON pin. A resistor R IMON is connected from the IMON pin to ground. So that's this resistor right here. The current flows through the resistor R IMON, creating a voltage drop across it. As the total load current increases, the voltage on the IMON pin increases proportionally. When the IMON pin voltage is greater than VOCP, the OCP will be triggered. Once OCP is triggered, it will be latched. Only restart up can release the latch. So basically, once you trip the total output current protection, you need to power cycle the card in order to get it to start up again. And this is like a pretty standard overcurrent protection implementation for this controller. Nothing, particularly special. And the fact that it latches is also standard. Like any card with a working overcurrent protection, it'll be latching. It won't start up again until you fully power cycle it. So anyway, the UP9511R will turn off both high side and low side MOSFETs of all channels. So that's, when it trips the overcurrent protection, the VRM basically just shuts down and the output voltage drops to 0. Now, because the VRM pretty much shuts down when the overcurrent protection is tripped, the symptom for this, if you're using the stock air cooler, is actually you're going to have your screen's going to go black because the GPU basically just got turned off. Or more like the GPU core just got turned off. But things like the fan controller on the GPU are still running, and if the fan controller isn't receiving any communication from the GPU core, it'll ramp the fans to 100%. Yeah, black screen with 100% fan speed is actually indicative of some kind of protection trip on a GPU. Not necessarily output current, like a total, not necessarily this protection right here. You could also be tripping like under voltage protection, over voltage protection, over temperature protection. Like there's a bunch of other protections on the card that could cause the exact same symptom of black screen, 100% fan speed, but OCP would do that. And the reason I point that out is because I really don't think it's possible for on air cooling for a 3090 to trick the overcurrent protection, which we'll get to. So anyway, turns off both high side and low side MOSFETs. The total OCP level is changed per actual operating phase number, so depending on how many phases are active, you get a different overcurrent protection. Table 4 shows the relationship between total overcurrent protection levels and operating phase number. The total output current of triggered OCP is calculated as this equation right here. So this equation right here tells us at what current draw the VRM will shut down. And so this right here is this VOCP is literally just from this table. So that's 3 volts. Our IMON is a resistor physically on the card that goes between the IMON pin and ground. So you can just measure that with your multimeter and get the value of it. N is the number of phases. R sum is another resistor physically on the card, which goes between, I can't remember, if we scroll up, so this resistor right here, that's our R sum. So that's the R sum resistor right there. And that's physically on the card as well, and you can just measure the value of that too. And then RDC is the DC current resistance of the inductors on the card. And for this, I have to take an educated guess because inductors have very, very, very low resistances. We're talking like fractions of a milliohm. And I don't have the equipment to measure that. So instead we're going to have to go with an educated guess for that. But anyway, so you can measure this, which is 11 kilo ohms. This right here is 392 ohms. And RDC, well, an educated guess for me is like 1 milliohm down to 0.5 milliohms. And honestly, the 1 milliohm side of that is kind of high. Because here we have, DigiKey, we have some inductors on DigiKey. These are 45 amps or higher sustained current ratings. And you can see the DC resistances here. Like the card uses 55 or... The 3090s use either like these 55 amp or these 60 amp power stages. Or I should say DRMOS components, but not that much of a difference. Well, technically all power stages are DRMOS components. Not all DRMOS components are power stages. So actually, no, it is a difference. But anyway, and you can see, so we have like 0.85 milliohms, 0.65 milliohm, and basically the more current an inductor can handle, the lower the resistance will generally be, because the higher the resistance the inductor is, the more heat it produces due to current flowing through it. So you don't really want to have high resistance inductors. That's bad for efficiency. And also somebody might be looking at this like 730 milliohms, that's really high. Yeah, that's a typo. Let me show you. Actually, I think if I just click on the PDF here. Yeah, so that right there is a typo, milliohms 0.73. Yeah, so that's just a typo from DigiKey there. So basically, my estimate of like 1 milliohm DC resistance is kind of high, right? Like it's pretty high. And then 0.5 milliohm is probably pretty close to what it actually is. And anyway, if you solve this equation, you end up, so if you solve this equation for a RDC of 1 ohm, I mean 1 milliohm, you get a current limit of 684 amps, which is generous considering that we have, 55 or 60 amp DRMOS components at best, and there's 10 of them. So already with a insanely high RDC value, the VRM current limit seems to be significantly above what the components can sustain continuously. But it gets worse because if we plug in an RDC of 0.5 milliohms, you get a current limit of 1,368 amps. There is no way the card is shutting down. Like, this will never trip. Because, like I said at the start, like 1 milliohm is actually really high. So realistically, this current limit has to be somewhere between like 800 and maybe 1200 amps, which pretty much means the VRM is not going to shut down, like, ever. Or by the time it shuts down, I think, well, no, it's just not going to shut down. Like, unless you have some kind of excessive cooling system. The reason why I say it won't shut down is because normally what happens when you overload a VRM and your overcurrent protection is set way too high, the VRM fails and the overcurrent protection never gets triggered, right? Which is why you could have, like, failed power stages and that kind of thing. If you just push too much current through them, they eventually just disintegrate. Anyway, so the overcurrent protection is somewhere between kind of high to extremely high. And so, well, yeah, okay, that doesn't surprise me too much. This is an NVIDIA GPU. Like, I'm not really aware of any NVIDIA GPUs that have reasonable overcurrent protection settings. Like, 980 Ti's don't have a reasonable overcurrent protection. GTX 590s don't have a reasonable overcurrent protection. I think the last card I've ever seen anybody complain about the overcurrent protection, and that even then it was only for extreme overclocking that they were complaining, was like the GTX 480. If you ran a GTX 480 on a reference PCB on liquid nitrogen, you would hit the overcurrent protection. But, like, there are so many cards after the GTX 480 where you wouldn't hit the overcurrent protection. It's so high that the VRM will fail before you get to the point of hitting the overcurrent protection. So the fact that this overcurrent protection on the 3090 seems to be absolutely, like, through the roof is kind of like, yeah, pretty standard NVIDIA design practices right here, as far as I'm concerned. And that's pretty concerning. Right. For comparison, most AMD GPUs will have their overcurrent protection set somewhat, like, at least reference designs from AMD will have their overcurrent protection actually set below the continuous current rating of the VRM. Because the thing is, like, technically, yeah, it's a 60 amp power stage, but if you actually ran 60 amps through it continuously, it'll get really freaking hot. Right? Like, really freaking hot. Like, this is 60 amps output. And at 500 kilohertz switching frequency, which the card doesn't run, it runs 300 kilohertz, I checked that. Like, we're producing like 9 watts of heat. This will, like, if you were running 600 amps through this VRM, it would be producing like 90 watts of heat. It's not sustainable, like, at all. So, yeah, anyway, the idea, though, I guess, from NVIDIA, like, I think the logic from NVIDIA for why they have these insanely high overcurrent protections is that it allows the card to have insanely high peak current draw without tripping the overcurrent protection, and the average power draw is handled by the shunt resistors. Now, the problem, but, like, that still just doesn't seem, like a sensible thing, because it's like, so you are designing the VRM to be at least somewhat overloaded on a semi-regular basis, right? Like, this literally, like, the way this overcurrent protection is set up is just like, yeah, we expect the VRM to actually get overloaded every so often. And the reason we're willing to be, like, we're tolerating that because on average it's going to actually stay within the power limit. And it's like, fine, okay. like sure, whatever. It's just like that seems like a very sensible way of running a card like this. Anyway, Let's move on to, so that's the overcurrent, total overcurrent protection, which basically is just like, as far as I'm concerned, it may as well not be there. Like, I don't believe that, because we have had people reporting that, like, playing New World, their card would shut down and the fans would go to 100%. And it's like, well, there's no way it's hitting 1,000 amps or 800. Like, if it's hitting 1,000 amps, then it's no mystery why these cards are failing. But I don't think that's even possible. Yeah, like I really don't think that's what's happening. I don't think we're tripping the total output current protection because it really does seem to be incredibly high. And so I find it very hard to believe that this would be the thing that's actually tripping. Unfortunately, I don't have like sacrificial test cards. Because what you could theoretically do is you could take one of these 3090s, you could just hook up an oscilloscope to the output of the IMON pin, and then just measure the voltage level on the IMON as it runs, say, New World. And yeah, if you catch the IMON voltage hitting close to 3 volts, like, oh boy. Like, that means, yeah, like, this thing's getting pretty maxed out. Also, one thing I find kind of funny is that you'll notice the this part of the documentation here. The IMON pin has a 0.6 volt offset voltage, which means the IMON voltage increases from 0.6 volts as load current increases. The resistor R IMON must be in the range of 10 kiloohms to 60 kiloohms to let the 0.6 volt offset mechanism work normally. The RIMON on the 3090 Vision that I have here is 11 kiloohms. Like, they could not set the overcurrent protection any higher. Like, it is basically maxed out. From the factory, they've maxed out the overcurrent protection. Yeah, so that's great. Anyway, let's move on to the channel current limit, as well as the channel current balance. So, I guess I'm just going to read through this as well, because I'm trying to restate this is not exactly easy. So the UP9511R senses phase currents for current balance by the means of on resistance of the power stage low side MOSFETs. So basically it uses the resistance of the low side MOSFET for measuring how much current is flowing through each phase. Now this is not super accurate, but it does have the advantage that whichever MOSFET is like crappiest is going to be loaded the least, because the controller isn't actually, like, the controller isn't aware of exactly what resistance each MOSFET has, but whichever MOSFET has the highest resistance is going to over-report current relative to the other MOSFETs in the VRM. So this will naturally sort of current balance the VR, like that'll help the controller maintain like peak efficiency on the VRM. So that's kind of neat. And anyway, the iSense X pins sense the corresponding phase current when the low side MOSFETs are turned on. So we have these iSense pins on the controller. They connect to the phase switch nodes using a resistor called RSense. And then we have this equation, which basically describes the sensed current relative to the phase current based on the RDS on VDC and RSense and the RSense resistance. Anyway. So where iSense is the sample and held phase current signal, the iPhase is the phase current, RDS on is the on resistance, so I literally just explained that. VDC is 30 millivolts as an internal voltage source, so this is basically just a little voltage offset due to how the controller functions. In this current sense mechanism, the value of the inductor current is sampled and held, therefore the equivalent sensed current can be described by the following equation. So this is if you wanted to convert that to the average current flowing through the VRM, because it doesn't actually measure average current, it measures the valley of the current flowing through the inductor. Because when you have a buck converter, the current through each phase ramps up and ramps down. So it measures the bottom of that ramp. Anyway, comparing between, so the sensed current I-phase SH is mirrored to the current balance circuit, comparing between each other and generating current adjusting signals for each phase. The current balance circuit increases the duty cycle of the phase whose phase current is smaller than the others and decreases the duty cycle of the phase whose phase current is larger than others. So basically, the important thing here is that this RSense resistance, depending on what it is, that sets the ratio. Like if you have if one phase has a higher RSense than another phase, that phase reports less current than the other phase. Now, this is significant because obviously we have this weird 8-phase VRM with 10 power stages in it. So we've got 2 phases where we've actually got 2 power stages in parallel along with 2 inductors in parallel. Incidentally, the power stage that blew up is one of the power stages in one of these parallel phases. So I don't know if there's a connection between that, like, because, sample size of one failed card is not enough to make a judgment. If it's always the same fail, if it's always a power stage in one of the teamed phases that is failing, then I'd say it's pretty safe to say that evidently the teamed power stages thing with an asymmetrical VRM like this isn't working properly. But as it is right now, I don't know if it's always the same power stage. If it is, then, you can make some judgments from that. As if it isn't, then it seems to be like, then I'd go with the theory of the VRM is just not powerful enough for what a 3090 actually requires. But anyway, where was I going with this? Yeah, so we have these different resistor values based on the current reading that you want to get for each phase. And so theoretically what you'd expect is you'd expect to have 2 different resistor values. The teamed phases have 2.6, would have like twice, would have 2 resistors, each being twice the resistance of the normal phases. And that would be that. And so what we actually have on the 3090 Vision is there is a bunch of phases with a 1.3 kilo ohm sense resistor. Then there's a couple phases with a 2 kilo ohm sense resistor, which doesn't make any sense to me. And then the teamed phases have a pair of 2.6 kilo ohm resistors, which makes sense. They have those phases are twice the size. They should handle twice the current. Therefore, they need twice as much. The resistor values would be twice as high. So that makes the resistor configuration for those makes sense. What I really don't get is why there's the 2 kilo ohm phases. Like, what is going on with those? I'm surprised it's not one of those that failed, because those would be underreporting their output current by a very significant amount compared to the other phases in the VRM. But it's one of the teamed phases that actually blew up. So yeah, I'm not sure. Like I do not understand the failure mechanism here, because if I had to guess what part of the VRM would fail first, it would be one of the 2 kilo ohm resistance phases. But that evidently hasn't happened to this card, at least. So yeah. Anyway, so the current sensing circuitry on this card is a bit weird. And now let's talk about the channel current limit. So the UP9511R adopts a channel valley current limit function to avoid catastrophic damage to the power stage components. I'd guess this is not set appropriately, considering that we had a catastrophic power stage failure on that 3090 Vision that I ended up repairing. The UP9511R monitors the sensed current at the iSense X pins. Yeah, we've read that already. If the sensed iSense of any phase exceeds the channel current limit threshold, the channel current limit function activates. The resistor R enable, so this is just a physical resistor, this is just a resistor that goes from the enable pin to ground, if I remember actually it just literally says it right there. Connected between enable and ground determines the channel current limit threshold. According to the mentioned current sense equation, the channel current limit equation can be written as 15. So, we have this equation. This is just a value that they give us. This is a resistor on the card that you can measure. This is another resistor on the card that you can measure. This is a value you just get given, right? VDC is an internal 30 millivolt offset, or internal 30 millivolt voltage source. Anyway, an RDS on. Now, this one's tricky because we don't actually have an RDS on spec for these power stages. It's just not really a thing. However, we can take an educated guess, again. And basically, I guessed that the RDS on of these power stages is somewhere between 2 milliohms and 2.5 milliohms, because these are 60 amp power stages. So to get, this level of efficiency, you would probably need something in that area of RDS on for the low side MOSFET. Anyway, so if you solve this equation for the 1.3 kilo ohm phases, you end up with a current limit of 80 amps. And for the teamed phases, the current limit is effectively 160 amps. And then there's the 2 kilo ohm phases, which for some reason have 130 amp current limit, even though they're only one power stage, which, I don't get what's going on with that. Anyway, if we keep reading, we want the actual what happens when you trip this overcurrent limit, because this is not a current protection, this is a current limit. So this actually limits how much current the VRM is going to output, which is super like this is a fiddly thing to have on a voltage regulator, because generally speaking, like the thing is, the amount of current the voltage regulator is outputting is basically directly tied to the impedance of the load that it's, powering, and the voltage that it's set to output. And you'll see what that actually causes, like here soon enough. So once the per phase current exceeds the channel current limit channel threshold, the per phase output inductor current is limited to an average current. If a continuous overload event may lead, oh, and then we've got the lovely English that you get from component manufacturers. A continuous overload event may lead the output, so a continuous overload event may lead the output voltage to drop and eventually trigger undervoltage protection and shut down the 9511R. So the thing is, if you start throttling how much current you're pushing into the GPU core, because basically the GPU core, when it's working really, really hard, it is the equivalent of having very little resistance. Right, so the amount of current that would, so if you want to feed the GPU core 1 volt, and it's working super hard, and its resistance is effectively really low, it's going to pull a ton of current at 1 volt. So if you have a current limiting function, which starts, reducing how much current you're pushing through the phases, your output voltage starts to drop, because either you have either you have 1 volt and some insane level of current draw, or you have less than 1 volt and a lower level of current draw. There's no other way to do this, right? Like you can't, or like the core would have to stop doing whatever it's doing in order for the the current draw to otherwise reduce. So the thing is, once this channel current limiting kicks in, basically the voltage starts to dip. And there's a programmed amount of tolerance for how much the voltage can dip before the voltage controller shuts down, because that means that the VRM is just completely overloaded. So here we have the undervoltage protection. The undervoltage protection is triggered if VFB is less than half the VEAP, so error amplifier voltage, sustained for 5 microseconds. When undervoltage protection is activated, the UP9511R turns off all high side and low side MOSFETs, and undervoltage protection is a latch off function and can only be reset by power cycling the controller. So basically, I think that when people play New World on 3090s and their 3090 shuts down and the fans go to 100%, I don't think they're tripping the overcurrent protection, the main overcurrent protection, because this is insanely high. I would expect the VRM to die before this trips. On the other hand, this could trip. This could actually trip. I could totally see this tripping on a sudden burst load from the GPU core where it just slams into the channel current limiting, which incidentally is set, 80 amps, 130 and 160 amps on the Vision card. So you slam into the current limiting, eventually the voltage drops so far down that the card either crashes, which is actually what'll happen. That's the consequence of it. But the thing is, I think NVIDIA has some kind of weird clock stretching thing for when the voltage starts to dip, because NVIDIA's approach to load line calibration is also super weird with their more modern GPUs. But yeah, so because here's the thing, if you start uncontrollably reducing the output voltage of the VRM because you're throttling back how much current it's outputting, the thing is, the GPU core or CPU or whatever, it needs some level of voltage to operate at whatever frequency it's operating at. And so evidently NVIDIA has some kind of workaround for that so that the card doesn't crash every time you hit the channel current limit. Otherwise, this would be completely pointless. This is actually a pretty modern, a unique feature as far as I'm aware. This is not, the channel current limiting, per phase overcurrent protection is a very common thing, where if one phase gets overloaded, then the VRM will actually just shut down. It's a pretty standard function that I've seen in other controllers, but this weird sort of if the phase gets overloaded, then we actually just start reducing the duty cycle of the phase. This is unique to more modern NVIDIA controllers as far as NVIDIA compatible voltage controllers, because like under most circumstances, if you start uncontrollably reducing the voltage, the chip is just going to crash, right? Like whatever you're powering is not going to get the voltage it needs to function correctly, and it's going to crash. But anyway, so NVIDIA has some kind of workaround for that. And so eventually it has to just hit the under voltage protection or the card crashes. If you're having like crash to desktop, that could be the channel current limiting pulling the voltage too low, but not quite low enough to hit the under voltage protection yet. And then if the card outright crashes completely and goes black screen 100% fan speed, I'm pretty sure that's just straight up under voltage protection tripping, because the overcurrent protection is so damn high. Like, it is so freaking high. I do not believe that it is possible for these things to be tripping that. Or if they are tripping that, then I guess it's no wonder that eventually the cards just outright fail. Because that's like, I think that one of the earliest reports about New World was somebody who had the card like hard crash 100% fan speed like a couple times in a row, and then the next time, actually maybe it was once, and then the second time the card just died completely. And it's like, yeah, so the first time it got it got massively overloaded and managed to shut down before any catastrophic damage occurred. But because of how insanely high, like even this channel current limit, like, with my estimates, this is somewhere around 80 amps for the low current phases. There's like 130 amps for some of them, and then the teamed phases are at 160 amps. And if you look at the documentation, and the reason why those current limits are set the way they are is because the alpha, like these DRMOS components from Alpha and Omega Semiconductor, they can technically tolerate 80 amp peak currents for 10 millisecond pulses. But the thing is, they don't mention how often. Like, how often can you survive a 80 amp 10 millisecond pulse, right? Also, like the 60 amp continuous current, like if the VRM is running really hot, this right here, and you get these massive current spikes that start slamming into like the channel current limiting, like that has to be wearing out the power stages incredibly fast. So, yeah. And then I guess on the like teamed phase, there might also be an issue with current balancing, because the voltage controller actually can't distinguish between the two power stages. Like it has no idea that these are two separate power stages. This, as far as the controller is concerned, this is one power stage and one giant inductor. And so if anything starts going wrong, like if one of these power stages gets overloaded while the other isn't, which is a weird situation to occur, because technically if one of those power stages is running significantly hotter than the other, it should have a higher RDS on, and it should it should naturally start pushing more current, like more of the current should flow through the other power stage that's running cooler. But even then, it's just kind of like if for some reason there's a major current imbalance in one of the teamed phases, like the controller's not going to know. It has no way to know. You could have like 100 amp current, like 100 amps flowing through one of the power stages and 60 through the other. And as far as the controller is concerned, this is completely fine. Which it's not for the power stages though. So yeah, like this is the thing that like this whole, like the way this VRM is set up is just kind of not safe. Not safe for the health of the VRM. And I imagine that the main reason NVIDIA does this is that, like, NVIDIA ultimately, handles the way NVIDIA handles power limits is that, on average, the card isn't going to go past its power limit, right? It's not going to exceed its average power limit. But the peak current draw that these cards can hit is insanely high. And it's also worth noting that, like, 3090s and, like, other high-end NVIDIA GPUs have very substantial input filters. Like, this is a lot of capacitance that they have here, right? So what the shunts are seeing, because the shunts are actually before the input filtering inductors, the shunts don't see the full, like, peak, like, they don't see the actual peak current. They see a reduced version of that, because that, like, the highest peak current is actually mostly pulled from the input filtering capacitors and is suppressed by the input filtering inductors, so that the actual, like, current monitoring circuitry that, NVIDIA uses for their power limit, that doesn't, like, it's not going to see those peaks. Like, that's the whole point of having it set up like this. And so the VRM, which does see the peaks, right? Like this thing could literally, like if this controller was configured correctly, like you could just have the channel current limit set to 60 amps and like 120 for the teamed power stages. Or if you went with like AMD's approach to setting current limits, you would actually have like a 500 amp current limit on the main output, and then like the total, like OCP would be like 500 amps or something, maybe 550. And then channel current limit would be like 50 amps, maybe 60. Right, you wouldn't have this like crazy high total output output current protection and also crazy high channel current limit. Which would, with the way NVIDIA has 3090 set up, like if you took a 3090 and just reconfigured these protection features to be more in line with the like continuous output rating of these power stages, I imagine the issue you'd run into is the card would be shutting down constantly under like pretty normal workloads. Like you'd be playing, I don't know, some like, so New World evidently has some crazy optimized part of the render where it just slams the core with work, which is hard to do. Like this is a really big chip with a ton of CUDA cores. So congratulations to the devs on figuring out how to use all that silicon to do something. But yeah, like, you know, you might be playing a less intensive game, which is still going to have really high peak current draws, and so that would potentially be tripping the safety features of the UP9511 like prematurely and constantly. And it would get really annoying. Like you couldn't play any games because the card would just be shutting down constantly. So, of course, the solution to the problem is, well, on average, we're only pulling like however much power. So we're going to set the current limits insanely high and sort of hope for the best. So yeah, I don't like the way this VRM is set up. Like as far as like maybe there's something I'm missing. But as far as I can tell, the output like ideally what I'd want to do is like take a sacrificial card and just monitor the IMON pin while playing like New World or well, probably New World, since evidently, because the thing is, there are workloads that can certainly, because the issue is you need to load slam, right? Because NVIDIA's power management is basically really slow, right? On purpose, like it's slow on purpose. You have the shunt resistors are all before the input filtering circuitry. So they're not going to see the peak currents whatsoever. It's just like they're not set up to do that. And then also the actual current monitoring chips themselves have like capacitors around them to filter to further filter the incoming like current sensing signals, so that they don't see crazy high, like that they see even less of the really high peak current draw. And so the thing is, so if you run like Furmark or something, it pulls an incredible amount of power, but it's a constant level of power, right? So that's really easy to throttle back because once you see it ramp up, you just slow the card down and you're fine. And then if you have the and games will have very high peaks in them, or at least I'd imagine Furmark is like throttled back, because I've run Furmark on the 3090 I've been fixing, and like, yeah, it throttles back really hard in Furmark. But I'd imagine if you had something that like momentarily hits the level of like core utilization of Furmark, the way that NVIDIA's power management is set up is just going to kind of let that go. Like, it's just going to let it go. And that's probably not great for the VRM. Because, yeah. Which would explain why you get, like, the random shutdowns, the 100% fan speed, like, all of that is basically just, like, evidently the card is pulling way too much damn power. And none of the protection circuitry is really set up. Like, well, no, the protection circuitry is tripping, but it's like, I think it's tripping a bit late. So, yeah. Anyway, so that's kind of my thoughts on the power delivery of the 3090. Now, this is still mostly speculation because I don't have more cards to test on to see how they behave. No, I don't even need more cards. Like, I'd need basically one sacrificial card. one sacrificial card, because I don't really, like, a lot of the things that would maybe give me more information is just, like, I don't really want to do it to somebody else's card that I need to return. Yeah, like, because I'm, like, I can't believe that the current limit, like, I have a hard time believing that the power limit would be as high as it seems to be. And there are ways to check that. It's just they'd be kind of intrusive. Because mainly what I'd like to see is, like, what is the IMON pin measuring? For that matter, I think you could also get a decent reading off of the, well, iSense pins, that's 8, like, I don't have an 8-channel oscilloscope, so I couldn't exactly monitor the per-phase current. Though I guess I could monitor a couple of the phases at a time and then switch over to the other phases, and yeah, but that would all be horribly, like, invasive measuring for a 3090, so yeah. Anyway, that's it for this video. Is just like, now at the, well, yeah, so this is my speculation on why the thing is, what I don't get is I'm pretty sure the current limiting is set up the same on most of the cards, like all of them. And so it's kind of weird that so far we've only had, like, some of the, like, we've had a lot of Gigabyte 3090 Vision cards fail. You know what? Screw it. This video is just going to keep going. Let's give up any hope of making this short. Because the thing is, here on Newegg, the 3090 Vision, like, it has a lot of really negative reviews. So, you know, cards stopped working after 1.5 months. 2 of these cards both died within 30 days. Card was correctly installed. Yeah, Screen goes black while playing Doom Eternal and never came back. No longer works at all. Go black. Yeah, so I had a few instances where my monitors would go black for a few seconds, then go back to normal. I attributed... Okay, that doesn't sound like overcurrent protection, because that would technically... Like, that should shut the card down completely, not just black screen for a bit. Card died on me less than 2 months of mild gaming. Unfortunately, I don't know what mild gaming is, so that's not really that helpful. Would be working fine until my monitors would just go black and fans rev to 100%. So that sounds like some kind of, like, that sounds like OCP or under voltage protection tripping. I had no way of using my PC until I held down the power button on the tower and restarted it. Yeah. But, like, the weird thing is like, why... So EVGA, with the FTW3 cards that were failing, they came out and said that it was faulty soldering that was causing the issues. And technically that would be able to trigger the... Well... No, it would technically be capable of triggering the protection features, because... What part of the datasheet is that? Right. Because the RDS on is the... Like, so that is a MOSFET that connects the switch node of the VRM to the ground of the GPU. Or, well, the switch node of its phase to ground. And the thing is, if you had crappy soldering, say in the ground connection, actually almost certainly the ground connection, because switch... Well, I guess you could also have it on the switch node end. Either way, let's say you had, like, crappy soldering. So the resistance of the solder between that low side MOSFET and the, between the low side MOSFET and ground, or between the, power stage and the switch node, because technically, like, you have an actual terminal for the low side MOSFET. You don't have one for the, where is it? I want to show you the pinout. Did I scroll past it? Oh, there we go. Yeah, so, like, here you have the switch node, and then you have the power ground plane, and so that big pad right there, that's the low side MOSFET connection, right? So if that connection, for whatever reason, was crappy, it would basically make the like it would make the RDS on look way higher than it actually is. So you could have like 2 milliohms of resistance in the MOSFET, but then like, I don't know, 10 milliohms of resistance in the solder, which would be a really, really crap connection. And that would technically trip the overcurrent, like that would potentially trip the overcurrent protection. But that would also make it trip super early, or at least it should make it trip super early. And I guess if you have a teamed phase where one MOSFET has like really crap soldering and the other one has perfectly good soldering, you'd have a ton of, like, basically a lot of the current would get shoved from the badly soldered MOSFET into the properly soldered MOSFET, and it would blow up the properly soldered MOSFET because the overall current limit isn't tripped. Yeah, that makes sense. Yeah, that does make sense. I wonder if that's actually the case. I don't know. Well, like that, yeah. So I guess that to me makes sense. Like that you could have one MOSFET which has such like especially like in the teamed phase, especially that's what should happen within my understanding. So that would explain why like crappy soldering would cause this kind of issue. I mean, generally crappy soldering would cause issues, but yeah, but then this is like a really widespread issue, and it's like why is it suddenly that 3090s are badly built? Right? Which to me just seems kind of like I don't know, maybe there was a like maybe there's a solder shortage and so now we have like crappy solder. um yeah, that's interesting. Anyway, where was I going with that? Yeah, so basically at the same time that would still because the thing is, like, so far, I mean, there's also the Zotac card. There's a video of a Zotac card burning up, trying to play New World. But there's not, like, I can't find evidence for, like, super widespread failure reports for the Zotac card. At least not as conveniently as the Gigabyte Vision here. Like, this is, you know, this is awful. You should not be able, like, I can't find this many negative reviews for any of the other 3090s and, like, 3080s. What is noteworthy is that, say this palette card, for example, and I've not really heard of any like palette cards going up in flames trying to run New World. And this would actually go up in flames if it failed, because there's no fuses on this. Similar to that Zotac card that smoked out. Like that video of the smoking Zotac card, like the reason that happened is because that card doesn't have any fuses. The Gigabyte cards and the EVGA cards all have fuses, so when they die quietly instead of spectacularly, but, you know... the failure, like what actually failed, is probably the same every single time. As in, like, it's always a failed power stage. I don't know that it would be the same exact power stage every single time. Anyway, where was I going with this? Right, yeah, so there's a lot of cards that use different controllers, right? Which, like, there's a lot of cards using the NCP 81610. But the thing is, the NCP 81610 basically uses the same kind of protection mechanisms. So if it's an issue of the protection mechanisms being set too high, why aren't, like, cards on the 81610 affected? Oh man, they don't have bold application information. Nope, this is all voltage control stuff. Switching frequency, new. Total current, yeah. Yeah, so you have IMON sensing. So I think this is like almost exactly the same. The total current sums the phase currents from each current sense power stage device in a single total current signal. The signal is then used to generate output voltage group, total current limit, and current monitoring output. Okay, no, that's just how the current monitoring works. Yeah, so I out pin sources a current in proportion to total output current. The voltage on the I out pin is monitored. Internal AD converter in should be scaled. External resistor to ground such that the load equal to system max current generates a 2-volt signal on I out. So different like voltage levels, but the theory of how this works is the same. Like, different implementation, but functionally it works the same. And this also has channel current limiting. Oh, here we have all the protections. Yeah, so over current limiting, under voltage protection. Oh, they've even joined these together because if you start bouncing off the overcurrent limiter too much, you eventually trip over, under voltage protection. The device incorporates per phase current limiting. Yeah, so we have all of that. Oops, sorry for hitting the mic. Yeah, so this is rather confusing to me because there's a lot of cards with the 9511s, right? Like if we go 3090, I mean the original FTW3s have the UP9511. The Gigabyte cards have the UP9511. The Zotac, this one has a UP9511, right there. Actually, this has even more UP9511s. Every single controller on this card is a UP9511. Now this doesn't have that second, doesn't have that 10th power stage, but that just means it could blow, like it'll just blow up some other power stage. Or maybe it'll blow up the same one. I don't know. It's just like I really wish I could take a look at the card that there's like a video of it smoking out. Because what I find interesting is it actually smoked out in the same area, like same general area as the Gigabyte card that I've been working on. I've worked on. It's reassembled and finished. I'm not going to do anything more with it. But anyway, yeah. And I also wonder, because the thing is, there's also going to be differences in like silicon quality. So maybe some of the 3090 cores just pull way more power than some of the other ones, which could sort of, stack into it. Like, unfortunately, not all silicon is exactly the same. So some of the 3090s might actually have like even worse current peaks than others. But yeah, the original FTW3 used a 9511, two of them, actually three of them, one for each rail. I think there's like a bunch of 3080s as well. There's no 3080 Ti's. Yeah, which is kind of interesting. And I don't know if we've heard of like 3080 Ti's failing in New World, but I've not yet seen a 3080 Ti with a UP9511. Right, like this Gainward Phantom card. This is on the NCP 81611 and 81610 as well. Yeah, 81610. Incidentally, this right here is wrong because the 81610 is an 8-phase, but the 81611 is a 4-phase. You can't, it's, I know it's NVIDIA, but they wouldn't use a 4-phase controller for a many power stage V-core rail. They're not quite that bad. Yeah, so like 3080 Ti's don't use those UP9511s, but the thing is, I still have a hard time believing that it's a fault of the UP9511 unless there was like some fundamental flaw in how the UP9511 implements its current balancing. Like maybe this is slower or just worse than what the NCP chips do, but that doesn't really like the thing is the 9511 this was specifically designed for NVIDIA cards. Like it follows the NVIDIA PWM spec, right? Like it says right here, supports NVIDIA's Open VREG Type 8 PWM vid technology, which I'm pretty sure. Oh wait, no, this is on NVIDIA OVR4i Plus. Wonder what the difference is then, because that is a newer spec as far as I know. Yeah, and the 9512 is on OVR4i Plus. Man, this isn't working. I was hoping to get like a PDF from NVIDIA instead of from UPI. Well, maybe UPI explains what it does. Let's try that. Oh no, they've changed their website again and it got worse. Yup, it actually got... Oh wait, no, this is some kind of like NVIDIA market, like UPI x NVIDIA marketing thing. 8-phase, supports smart power stage. Oh, I think that's the only difference, is that it's like smart power stages instead of just dumb power stages. Oh no. And this video has gone totally off the rails at this point. I give up. Anyway, Yeah. And one thing I'm kind of wondering is like, okay, so maybe right now what we're seeing is like the worst implemented cards failing first, or like the cards that got, drew the short straw when being manufactured. Because there is manufacturing like variance, right? In the silicon, to some extent in the soldering quality, as we've apparently found out. Um, and so the thing I'm wondering is like, okay, so maybe 3 years from now, we're gonna just see a flood of 3090s with dead V-core. Because that kind of like that happened for like say GTX 980 Ti's. Like it's really not that difficult to find GTX 980 Ti's with dead V-core VRMs. Um, and honestly, the 980 Ti's I don't think are even that underpowered. Like the VRM on those is not great, but it's not that terrible. Um, then again, I guess like 980 Ti's are also like the first cards to use a really, really aggressive boost system. So maybe those already sort of started approaching the territory of what the 3090s are doing, of like really massive transient loading. So while the VRM is like on like for average current, it's technically fine, but then peak current, it's not fine at all. Um, but yeah, so that's the thing, is just like, so I don't have a like conclusive answers here. Um, because I just lack a lot of information. Like I don't actually know what the peak current draw of a 3090 is when playing New World. It's probably insanely high. Um, because otherwise I don't know how it would be killing power stages, right? Like, yeah. Um, and then the other thing is like, yeah, I just don't know. Like, I don't have an answer, and I'm really annoyed about that because it's like, I think most people, when they watch a video like this, they're hoping, hey, he's gonna have an answer. And it's like, nope, I ain't got no answers because I have one card. Most of what I figured out with the one card I have is like, okay, this is not gonna shut down if something goes wrong. Or more like, if things are going wrong, this isn't gonna shut down, is the better way to put it, right? Like, if the VRM is outputting 700 amps for a moment, it's not going to shut down. If the channel current limit is, some of the phases are getting slammed with 80 amps, ain't going to shut down. If some of them are getting slammed with 160, ain't going to shut down. Um, like, yeah. Which is still, like, which makes it even more confusing that there's cards that do shut down, right? Playing New World. And I'd say definitely if you play New World and your card shuts down, black screen, 100% fan speed, lower the power limit. Lower the power limit a lot. Like 30, 40% maybe. Because the control, like, yeah, like there's just no safety features built into the card. Like this is actually, that's the thing that annoys me the most with this whole discussion of New World, is like people being like, oh, it's the New World is circumventing some software level power safety. And it's like, if your power limit, if your VRM protection features are implemented at the driver levels, that is a problem, right? The driver should not be handling things like output current protection because it's built into the freaking controller. Just don't set it up with the RI mon as low as it freaking goes, right? So yeah, technically you could replace this resistor with like, I don't know, 15K or something to drastically reduce how much current, like massively reduce how much current the VRM is going to allow the GPU core to pull. But the problem with doing that is the card's going to randomly shut down under like normal usage potentially. Which, yeah, like this is just like, no, what you actually want, like the proper solution to this problem is a bigger, better VRM. It's not like, yeah, bigger, better VRM or a more power efficient GPU. One of those two. Not like, oh, I'm just going to have the card shut down more frequently. Like, that would certainly be safer, right? Like, if the VRM shuts down before any of the components are getting overloaded, then of course it's not getting overloaded. It shouldn't fail. It's just kind of like, it also makes the card borderline unusable because it shuts down anytime you try to play a game. So, yeah. That's kind of it for this video, I think. Man, it's an hour. But like, yeah, I don't know what else to say about it. It's just like I'm not like maybe I missed something, but within my understanding of power delivery, the way the power delivery is handled on a 3090 is basically cross your fingers and hope that nothing goes wrong. Because if something goes wrong, the controller is not going to shut down. It's just going to sit there and watch the VRM, like the MOSFETs, destroy themselves. At which point, at least with the Gigabyte cards, you do have, input protection or board protection fuses. Those fuses aren't there for your power supply. Those are there to make sure that when a power stage fails, it doesn't put a crater in the PCB. That's what those fuses are for. They're not there to prevent the power stages from failing, because the power stage is going to go and then the fuse is going to go. But at least it's not going to take the PCB with it. But yeah, so there, that's it. An incredibly rambly video about the power delivery of at least, like, I think this design is going to be shared by most of the UP9511 based cards. Maybe all of them. I don't know. Like, technically speaking, there's nothing preventing a manufacturer from taking a 9511 and just not implementing this with a 11 kiloohm freaking RIMON pin. It's just, I'm also not sure how they make sure those cards actually function in regular usage. So, yeah, that's, like, that's fun. Anyway, there. That's actually it for the video. I guess thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comments section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTuber merch. Both Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you'd check them out. Yeah, that's it for the video, so thanks for watching, and goodbye.